Hi, hello, good afternoon, everyone. So in this class, I'm going to deal you regarding two compartment open model IV bolus administration. Two compartment open model IV bolus administration. So as the name suggests, it is two compartment open model IV bolus administration. That means it will be containing two compartments. As you can see here, there is a central compartment and there is a peripheral compartment. Two compartments. The drug is distributed between two compartments, that is central compartment and peripheral compartment. So from central compartment, the drug will be distributed through K12 constant to peripheral compartment. From peripheral compartment, the drug is distributed to central compartment through K21. So K21, what is 2 here? 2 is the peripheral compartment, 1 is the central compartment. And here you can observe, unlike one compartment open model, there is no absorption constant here. There will be only elimination constant, that is Ke. And when you plot a graph for this, the log C on y-axis and time on x-axis, the central compartment line on this graph will be like this. There will be rapid decline during the initial phase and there will be slow decline during elimination phase. So that is why the line will be like this. In the distribution phase, the decline of the drug will be rapid, and in the elimination phase, the decline of the drug will be slow. So that is the central compartment graph line. And when you take peripheral compartment, you see here, peripheral compartment graph follows a parabolic path. This is the parabolic path. Initially, the drug concentration is 0 in the peripheral compartment. So that is why the line starts at the initial phase. And then the line moves when the drug increases its concentration, the line moves like this and declines during elimination phase. So that is why the peripheral compartment graph will be parabolic, like one compartment open model oral administration and extravascular administration. This is like one compartment open model oral administration and extravascular administration. But when you take the central compartment graph, the graph line will be a straight graph line will be seen. You can see here, where in the distribution phase, the drug will be rapidly declined, and in the elimination phase, the drug decline will be slow. So that is why it follows a line like this, the central compartment drug line. And when you take the equation, the rate equation for this two compartment open model IV bolus, that is dCc by dt. Cc, why it is called as Cc? We are considering only central compartment. So that is why dCc by dt, the rate equation is equal to, you know the formula of the rate equation, that is rate in minus rate out. The drug rate in minus the drug rate out. So here you see for the central compartment, from where the drug is coming from the peripheral compartment. The drug is distributed to central compartment from peripheral compartment. So what is rate in here? The rate in constant will be this one, K21. Why? Rate in means what? The coming of the drug, incoming of the drug. So from where it is coming? From peripheral compartment it is coming. So that is what K21 is the constant here. So that is why dC by dt is equal to K21 into Cp. Cp is the, from where it is coming from the peripheral compartment. The concentration of the drug coming from peripheral compartment. So that is why Cp minus rate out. So rate out, how the drug is going to eliminate from the central compartment? In two ways it is eliminating. In the first way, the drug is going out from the central compartment and it is reaching peripheral compartment. That is the constant K12. So that is, you can see K12 Cc, that is central compartment. And then the next thing is Ke. Here it is eliminating from another route that is called as Ke, elimination constant, that is Ke into Cc. So like that, the rate constant equation will be established for this two compartment open model IV bolus. Again, you see, that is dCc by dt is equal to, as the equation, rate in minus rate out. Rate in means incoming of the drug. to the central compartment. From where the drug is coming? The drug is coming from the peripheral compartment. So that is what is the constant here? K21. So that is K21 into Cp. Cp means what? Peripheral compartment concentration minus rate out. Rate out means the drug is going out from the central compartment. From how many ways the drug is going out from the central compartment? You can see here. The first way is from central compartment, the drug is going to peripheral compartment. The constant is K12. And the second way, from central compartment, it is totally eliminated out. That is Ke, elimination constant. So Ke into Cc. So that is the equation. dC by dt is equal to K21 Cp minus K12 Cc plus Ke in Cc. That is rate in minus rate out. So in terms of X, if you write in terms of X, X means what? Volume of drug. If you write in terms of X, what is the X formula? You know very well that Vd is equal to X by C. Then X is equal to what happens then? Vd by C. Then C is equal to what happens? X by V. So that is why it is written as dC by dt is equal to same K21 into C means what? X by V. That is xp by vp minus K12 into same C means xc by vc minus Ke into C means what again? X by xc by vc. So like that it is written. And then when you take the formula of peripheral compartment, up to now we have known regarding the formula of only central compartment, rate equation of the central compartment. Now we are going for rate equation of peripheral compartment. So the formula will be same, that is rate in minus rate out. So to the peripheral compartment, from where the drug is coming, rate in. Rate in means what? Incoming of the drug. From where the drug is coming? From central compartment the drug is coming. That is what? K12 Cc. K12 Cc. Then minus rate out. Rate out means what? Where the drug is going to eliminate. Here, through only one route the drug is eliminating. That is what is? The drug is from peripheral compartment, the drug is eliminated to central compartment. That is, drug is going out from the peripheral compartment to central compartment. So that is why it is given as K21 Cp. Always you remember rate equation means rate in minus rate out. So here again you see in the peripheral compartment rate in means incoming of drug. From where the drug is coming? The drug is coming from central compartment. So that is why it is called as K12 Cc minus rate out. To where the drug is going? The drug is going to central compartment, K21. That is K21 into Cp. So that is the rate equation formula. Again, when you consider in terms of X, when X is equal to, then what it becomes? K12 into Xc by Vc minus K21 into Xp by Vp. So that is the another rate equation. Next, so when you do integration as we have done for the one compartment open modal IV bolus and one compartment extravascular administration, when you do integration for central compartment rate equation and peripheral compartment rate equation, we will get this formula or this equation we will get. And here K12 and K21 are the transfer constants, and bolus doses, and alpha and beta are called as hybrid constants. Alpha and beta are called as hybrid constants. Here it is the formula you have to remember. And alpha can be noted as A and beta can be noted as B. So alpha can be written as A and beta can be written as B. So when you take in an exponential form, it becomes A into E power minus alpha t plus B into E power minus beta t. So that is nothing but distribution exponent will be A into E power minus alpha t plus elimination exponent will be B into E power minus beta t. Here you always remember A and B are alpha and beta are hybrid constants. And this equation can be done by using method of residuals formula. As we have done it in the one compartment open model, method of residuals formula, here C is equal to A into E power minus alpha t plus B into E power minus beta t. According to method of residuals, the distribution is more here. Distribution is more in the two compartment open model. So when the distribution is more and the distribution is more faster than elimination, then alpha will become greater than beta. So alpha is an distribution coefficient, automatically it becomes more greater than beta. That means nothing but alpha will reach infinity, that is 0. So the equation will become only BE minus BT. As the alpha is infinity, it becomes 0. So in the equation, there is only one thing remains, that is elimination constant, that is B into E power minus BT. And when you take logarithm of this equation, then it becomes log B minus BT by 2.303. So when you do logarithm, and we will get these equations. And when you take graph, and when you take an x-axis minus alpha by 2.303, that is logarithmic value. And when the y-axis, when you take log concentration, and this is the graph we will get. And from the graph, we will get the formulas like C0, elimination of life, K12, K21, and also area under curve. So these are the formulas which we will get from the graph. So this is about two compartment open model IV bolus administration. So any derivation, any equation, it requires practice. If you practice it once or twice, then you will get it very easily into your mind. Compared with the theoretical representation, practice is highly important for these derivations. Thank you.